13.1 Sequences and Summation Notation. A sequence is a function f whose domain is the set of natural numbers. The terms of the sequence are the function values f of 1, f of 2, f of 3, all the way until f of n. We usually write a, we say sub n because it's in the subscript, a sub n, instead of the function notation f of n. So the terms of the sequence are usually written as a sub 1, a sub 2, a sub 3, and so on. The number a sub 1 is the first term, a sub 2 is the second, so then in general, a sub n is the nth term. So a sub 40 is the 40th term. Whatever the number is that's down in the subscript is going to be that number term. Informally, we can say that a sequence is just an infinite list of numbers. The numbers in the sequence are often written, like I said, as a1, a2, a3. And the ... at the end just means it continues on. So for example, we could see the sequence 5, 10, 15, 20, 25. I mean, we all know the drill. That's the first number, the second number, the third, the fourth, and the fifth. That's what those are really standing for. So the pattern above can be described as going from one number to the next by adding 5, right? We can also say that it is the formula a sub n is equal to 5 times n. So n being this number. So 5 times 1, 5 times 2, 5 times 3, and so on. We can also write this as what we call the recursive formula. So for this recursive formula, we take the term prior to it and do something. So a sub n minus 1 just means the previous term. So to get the next term, we take the previous term and add 5. So to get 10, we said 5 plus 5. To get 15, we said 10 plus 5. All right, so another example would be 2, 4, 6, 8, 10, and so on. So what's the pattern? I mean, obviously we see that we're counting by 2s, but what's going on here is that we could say the pattern is adding 2 each time. The formula, so that would mean a sub n is equal to, remember this is the first, the second, the third, the fourth, the fifth. I can say I'm multiplying 2 by 1, 2 by 2, 2 times 3, 2 times 4, 2 times 5. So 2n, whatever the n is, that's the number of the term. The recursive formula would be saying that we're using the previous term. So the previous term plus 2 is going to give us the new term. And now we want to find the 103rd term. Well, it'd be crazy to keep counting until we got there. We'd be here for quite some time. But what we can do is use one of these formulas. So we can do a sub n is equal to 2n, probably the easier one to do. So we'd say a sub 103 is going to equal 2 times 103. So we're going to get 206 for that, whoops, not 26, 206 for that 103rd term. All right. So let's find the terms of each sequence. Find the first 5 terms and then find the 100th term of the sequence defined by each formula. All right, so to find the first 5 terms, we're going to plug in 1, plug in 2, plug in 3, and so on. So if I want a sub 1, that's going to be 2 times 1 minus 1. That's going to give us 1. A sub 2, that's 2 times 2 minus 1. So 4 minus 1 is 3. A sub 3. 2 times 3 minus 1, so 6 minus 1, a sub 4, we also want a sub 5, so 2 times 4 minus 1, 8 minus 1 is 7, and 2 times 5 minus 1, 10 minus 1 is 9. All right, and the last thing that we want to do is find the 100th term, so that's a sub 100, we're going to do 2 times 100 minus 1, so 200 minus 1 is going to give us 199. Okay, we could do the same for the rest of these. So C, A, doesn't matter what the letter is. To find C sub 1, we're going to do 1 squared minus 1, so that gives us 0. C sub 2, that's 2 squared minus 1, 4 minus 1. C sub 3, so we're going to get 3 squared minus 1, and we're going to get 8. C sub 4, we're going to get 4 squared minus 1. That's going to give us 16 minus 1, so 15. C sub 5 is going to give us 5 squared minus 1, so 24. And C sub 100 is going to give us, 100 squared minus 1. That's going to give us 9,999. All right, you may want to pause this video and try the next two. All right, so let's take a look at these next ones. Same concept, we're just going to plug in 1, plug in 2, plug in 3, and so on. That's 1 over 1 plus 1, so we're going to get a half. T sub 2 is going to be 2 over 2 plus 1, so that's going to give us 2/3. T sub 3, that's 3 over 3 plus 1, so we're going to get 3/4. When we get to the rest of these, I know you can do the arithmetic here. That's going to give us 4/5. T sub 5 is going to give us 5/6, and T sub 100 is going to give us, let's see, 100 over 101. And then we can use the same rules here. R sub 1, so that's -1 to the first over 2 to the first. That's going to give us -1/2. R sub 2, we're going to get -1 squared over 2 squared, so that's going to give us +1/4. R sub 3, that's going to give us -1 cubed over 2 cubed, so -1/8. R sub 4, that gives us -1 to the 4th over 2 to the 4th. That's going to give us 1/16. R sub 5, -1 to the 5th over 2 to the 5th, so -1 over 32. Notice we bounced back and forth between the pluses and the minuses here. And then R sub 100 is going to give us -1 to the 100th over 2 to the 100th. It's going to be a nice big number, positive on top because that's an even exponent, and we'll just leave it as 2 to 100. We'll run out of space if we actually multiply it out. Right? It's often useful to picture a sequence by sketching its graph, though. So since a sequence is a function whose domain is the natural numbers, just the ones we're counting with, we can draw it using just the regular xy plane. This is just like what number term we're on. So first term, second term, third term, fourth term, and so on. And then the actual value of the term is on the side. All right, so for example, we see this graph here. Really think of this as my x being 1, 2, 3, 4, 5, 6, and so on. And my y is really the value here. Okay, so this is really my n and my a sub n. All right, so we see that these terms are decreasing, which makes sense. 1, 1/2, 1/3, 1/4, 1/5, and so on. And then let's take a look at this next graph. Notice we go positive, negative, positive, negative, positive, negative, back and forth. Notice the graph does kind of a zigzag going back and forth on opposite sides of the x-axis. So that's kind of something to notice, that it's not connected at all. We do see that back and forth pattern when the signs alternate. So we want to notice that these are not connected. We call these discrete. There's no in between these numbers. In example 2, we're asked to find the nth term of a sequence whose first several terms are given. So here we see a half, 3/4, 5/6, 7/8. When we're doing this, we really want to look at the numerator and denominator separately to try to find a pattern. So we should notice that up top we have all the odd numbers, and on the bottom we have all the even numbers. So if we were to start with the even numbers, it looks like whatever term we're on, we're just multiplying it by 2, right? 1 times 2, 2 times 2, 3 times 2, 4 times 2, and so on. So when I'm trying to look for my pattern, remember this is the first, second, third, fourth. In the denominator, we have 2 times whatever number term it is. Up top, the odd numbers look like they're of the form 2n minus 1, just one less than the denominator. And an odd number is going to differ from an even number by exactly 1. So that 2n is representing the even number, and then we're taking 1 away from it. So there's our formula. We want to find the nth term. This is the nth term. Our formula basically is the nth term. Here we see -2, +4, -8, +16, -32. So what we want to make sure that we're doing first is looking at the negative. In order to alternate signs, we need to make sure that depending on the n, whether we're going to get a positive or a negative here. So the first term is negative. What that's going to tell me is if I have an odd numbered term, 1, 3, 5, that I get a negative, use an exponent. So -1 to the nth power, when it is an odd n, it's going to be negative. When it's an even n, it's going to be positive. Okay, and then to get that 2, 4, 6, 8, 1 times 2, 2 times 2, 3 times, or sorry, 1 or 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth. So times 2 to the n power. Okay. All right. And really, we could rewrite this. We could say this is negative 2 to the n, and that would be acceptable as well. Recursively defined sequences. Some sequences do not have simple defining formulas, like the ones before this. The nth term of the sequence could depend on some or maybe even all of the terms prior to it. So a sequence defined this way is called recursive. To find the first 5 terms, we're going to be told what the first term is and what the formula is. So in order to use the formula, we need to know what the term is prior. So the first term is given to us. We want to find the second, third, fourth, and fifth. In order to do so, we have 3 times the previous term plus 2. So we're going to take this previous term and plug it in. That's going to give us 3 times 2, or 3 times 3, so we're going to get 9. And we're going to do the same thing. So 3 times the previous term plus 2. We're going to plug that 9 in. So 9 and 2 is 11, times 3 is going to give us 33. All right, so it's 3 times the previous term plus 2. We're going to take that previous term, 33, add 2, get 35, and then multiply, we're going to get 105. And then again, 3 times the previous term plus 2. We're going to plug in 105, and then we're going to get 321. So far we have 1, 9, 33, 105, 321, and so on. Here we have something called the Fibonacci sequence. We want to find the first 11 terms, and there's a reason for this. So the first 11 terms, we're going to use F for Fibonacci here. F1 is 1. F2 is 2, is also 1. F3, so now we're going to plug in. So we need to use the 2 previous terms to add together. So it's the previous term, and then the term 2 before. Okay, so the first term is 1, the second term is 1. Here I'm going to do, really this is going to be F2 plus F1, and I'm going to get 1 plus 1, I'll get 2. And now for F of 4, or Fibonacci number 4, we're going to do F3 plus F2. So 3 is the number 2, 2 is 1. If we do F5, that's going to be the previous one plus the one before that. So that's going to be 3 plus 2, we get 5. So we're going to get this sequence. It's going to continue on. F of 6, we're just adding these together, we'll get 8. F7, we're going to get 8 plus 5. We're going to get 13. F7. F8, 13 and 8 is going to give us 21. F9, 21 and 13 is going to give us 34. F10 is going to give us 55 when we add 21 and 34 together. And F11 is going to give us 34 and 55. We're going to get 89. Okay, this is our Fibonacci sequence. The sequence in this example we just said is called the Fibonacci sequence, and it's named after the 13th century Italian mathematician Fibonacci. He used it to solve a problem about specifically breeding rabbits. And this sequence also happens to occur in nature in a few different places. So there is this sort of perfect spiral, looks like a special shell here, and it has that special pattern within it, 1, 1, 2, 3, 5 in that spiral. We also see something called the golden ratio, which has a lot to do with Fibonacci's sequences as well. And if you've ever kind of explored some of this maybe in middle school, you'll see that there is sort of a perfect ratio where things just look, well, perfect. It looks nice to the eye when you see a rectangle of a certain form, and that's how a lot of things back in ancient Greece were built based off of this golden ratio that has a lot to do with our Fibonacci sequence.